Okay, the last example that we have here is solving another triangle. This time you're given the information, you're not given a diagram. And so we're told angle x is 68 degrees, little y is 7.2, and little z is 8.3 meters. And so one of the things to recognize is because it doesn't tell you that there's a 90-degree angle, you can't assume it's a right angle triangle. So what I'm going to draw is an acute angle since the angle that I'm given is less than 90 degrees. So here's my triangle. I'll call this x and label it 68 degrees, and then y and z. And then I'm going to label the side lengths that I'm given according to the angle that's given. So 1 second. Alright, so I'm going to label it according to the side lengths that are given. So little y is going to be across from angle y, so this will be 7.2 meters. Little z will be across from angle z, so this will be 8.3 meters. Okay, so I'm given angles, side, which means I cannot use the sine law. I don't have an angle in its opposite side, so I don't have a pair that I can use in order to use the sine law. So instead what I would have to use is the cosine law. And so looking at the information that I have, in order to make a complete pair, what I'm going to try to solve for is little x, which is across from angle x. Okay, so remember what the cosine law used to look like. A squared equals b squared plus c squared minus 2bc cos of a. So there's the cosine law. And this cosine law is used when you're solving for a side length. And coincidentally, I am solving for a side length here. So I'm going to rewrite the cosine law using the variables that I have. And so I'm going to try to solve for little x. Okay? That's one of the things you need to recognize. The other thing I want you to list, if you can, is all the information that you do need to find. I'm not going to list the information that I'm given because that's already listed over here. So what I do need to find is little x. I need to solve for angle y, and I need to solve for angle z. So that's all the information that I will be finding eventually. So for x, little x, side length x, what I'm going to be using is the cosine law. So x squared equals y squared plus z squared minus 2yz cos of angle x. Remember that the side length and the angle that you are looking at are as far away from each other as possible in the equation. And I'll plug in the information I know. So I have 7.2 squared plus 8.3 squared minus 2 times 7.2 times 8.3 times the cos of 68 degrees. And I'm going to do all of the calculations here in one step. That'll ensure that my solution is accurate. So 7.2 squared plus 8.3 squared minus 2 times 7.2 times 8.3 times the cos of 68 degrees equals, and that gives me about 75.9570. And now to solve for x, I need to find the square root of both sides. And so I get approximately 8.7 meters. Okay, so I got about 8.7 meters for that side length there. Okay, so what else do I need to solve for? I need to solve for angle y and angle z. And in order to do that, now if you notice the information that you have, we actually have an angle in its opposite side, which means now we can start using the sine law. And that's exactly what we're going to be doing. So in order to solve for angle angle z and angle y, we're going to be using the sine law. Okay? So let's look at the first part. So let's start by looking at angle y. So for angle y, I'm going to be using the sine law. Because I'm solving for angle y, what I will do is start by writing the sine law with angle y. So sine of angle y over little y equals. Now the right hand side of this equation will end up being the sine of the angle that we have and the side length that's associated with it. So the angle that we have is angle x, and we have little x. So that's the complete pair. That's going to go on the right hand side. So sine of angle x over little x. And then from here you're just going to substitute in your information and try to solve for angle y. Ideally what you want to try to do is put the variable that you're solving for in the numerator. It just makes your work a little bit easier. So sine of angle y over 7.2 equals sine of 68 degrees over 8.7. That's the value that we just solved for. And then, again, I'm going to try to solve for sine y. The easiest thing to actually do, because y is already in the numerator, is to just multiply both sides by 7.2. And what that'll do is cancel out the 7.2 on the left-hand side, and I get sine y is approximately equal to, and if you notice on the right-hand side, those are all numbers that you can actually just evaluate. So I'm going to look at the sine of 68 degrees, multiplied by 7.2, and then divide by 8.7. And so I get about 0.7673. I can solve for the inverse sine here to get y, so I can find sine inverse. And so angle y is approximately equal to 50 degrees. Okay, so there's angle y, that's about 50 degrees. And I'll label that in the triangle as well. It just makes your work a little bit easier. It helps you recognize if there are easier ways to solve for certain parts of the question. And so the last thing I need to solve for in order to solve this triangle is angle z. And there is actually an easy way for you to do this. And that's using the sum of the angles in a triangle theorem, which means you're going to subtract the two angles that you have to solve for the third angle. And you're going to subtract them from 180 degrees. So angle z is equal to 180 degrees minus 68 minus 50. And angle z would be approximately about 62 degrees. And these are all approximations because that's round everywhere. And so, quick way again to check your work. Smallest angle should be across the smallest side. So here's our 50-degree angle. There's the smallest side that we have. Largest angle, so that's a 68-degree angle, should be across the largest side. And that's exactly what we have. Okay, so this was an example of an acute triangle. It wasn't a right angle triangle, so we couldn't use Pythagorean theorem. We could not use SOHCAHTOA either. We had to use the cosine law and the sine law and some other things that we know from grade 9. So like the sum of the angles in a triangle theorem. Okay, that's it.